In this video, I'm going to talk about stationary states. This video is part of a playlist on quantum mechanics. You can find the link to this playlist in the description below. So in the previous few videos, we've used the method of separation of variables to solve the Schrödinger equation. And the solutions that we actually found were separable solutions. But not all solutions are separable. Let's have a look at separable solutions first, and then in later videos, we're going to talk about the superposition of separable solutions, when we actually add multiple separable solutions together to construct a general solution to the Schrödinger equation. So first of all, let's have a look at what we managed to find by solving with the method of separation of variables. So we found solutions of this form. So psi of x and t is equal to little psi of x times phi of t. So this is, by definition, a separable solution. And by solving an ODE, which we got from the method of separation of variables, we managed to ascertain this guy, and it was actually an exponential function. So we can rewrite this as psi of x times e to the minus I capital E, that's the energy, over h bar and t. So this is the time dependence of the solution. So this is what separable solutions look like. This guy over here, this lowercase psi of x, this solves the time independent Schrödinger equation. And that's actually what the last video was about. It's the time independent Schrödinger equation and how we can solve that by specifying v of x. So this over here is the general form of a separable solution. Something that's very special about separable solutions is that they are stationary states. So how can they be stationary states if there's a time dependence? Right? This is changing with respect to time. But let's have a look at the probability density. So the wave function is changing with respect to time. You can imagine it's oscillating, right? It's oscillating in the complex plane. But this probability density function that we can actually get from the wave function, it does not depend on time. I'll show you what I mean. The probability density function is defined to be capital psi of x and t. I'm going to take the absolute value and square it, right? And that's, how do we actually get this probability density function? Well, we take psi star, or the complex conjugate, and we multiply it by psi. So how are we going to complex conjugate this? Well, we're going to have to take all of the i's and turn them to minus i's. And all of the minus i's, we're going to turn them to plus i's. So we just change the sign of the imaginary component. This over here, we can actually expand and we can rewrite it using this up here. So what we're going to get is on the left, so this complex conjugate is going to have psi of x. It's going to be complex conjugated. And then we're going to have e to the plus I e over h bar t. You see what I did here? I turned this I into a plus I because there was a minus sign over here. So minus turns to plus when we complex conjugate. And this guy is also a complex conjugate because it can actually be a complex valued function. It doesn't have to just be a real valued function. Then what about this psi? Well, that's just going to be this. So we're going to have psi of x times e to the minus e, and this is a capital E over h bar t. And we can see that there is a pattern over here. This conjugated psi and this unconjugated psi are analogous to these guys over here. So we can group them together. And this exponential and this exponential, we can group them together. And you can see that they have the same exponent, there's just a sign difference. Using exponential laws, we can combine these two guys. And when you multiply two exponentials, what you can do is you can actually add their exponents. If we add these guys together, we're going to get 0, right? Because this is the positive and this is the negative. These guys are going to add to give 0. So what this is actually going to turn into is e to the 0, right? Because we're adding these two guys. E to the 0 times the complex conjugate of this lowercase psi times psi of x. So that's what we're actually going to get. And this is just equal to 1, right? E to the 0 is 1. And this is just the same as the absolute value of psi of x squared. right? Using the same reasoning over here. This is the probability density function, and this over here is the complex conjugate times the wave function. So using that same reasoning, we can work out over here that this guy is just dependent on position. So there's just a position dependence, just an x dependence. There's no dependence on time. So this is actually a stationary state. This is only true for solutions of this form. So only solutions of this form where you can actually separate them, separable solutions, they are going to behave like this. For other solutions that are a sum of these types of solutions, they're actually not going to cancel. All of these exponential factors aren't going to cancel. So we're going to get some time dependence remaining in the probability density function. But these guys are special, and that's why they're called stationary states. So these separable solutions are stationary states because the probability density function does not depend on time. That's the most important takeaway message from this video. So another interesting thing that you can always observe is that there are analogous patterns occurring that we can keep reusing. And that's what we did over here. We saw that this pattern, where you have a complex conjugate times the function, is equal to the magnitude of the function squared. That we used again. So we used it in this direction to open up this function and repackage it, and then we used it to condense it together again and repackage it like this. So this is equivalent to the probability density function if you're dealing with a stationary state. We're going to keep talking about this type of stuff in quantum mechanics in later videos of this playlist. You can watch all the videos in this playlist if you click over here.